So, hello everyone. This is India Uniform 2 Kilo India November, Niccolò. I'm part of the OpenRTX team, and this morning or evening, according to your time zone, we'll be trying to do a live implementation of basically of the remaining part of the modulator in M17 just to, for example, give a bit of visibility outside of what is basically what is how the modulator is done, and maybe we could also get some feedback from the public in the chat. So here with me there is also Wojciech. Um, which joined me in a call, so he will be helping me in troubleshooting everything and making everything work. Okay, so Wojciech, you should now be connected to the stream. Okay, so basically, where we are right now, where are we? So let me open up my file so that we can show something. Okay, I had this. So, basically, what we are trying to, I don't know how many viewers we have. We already have. Okay. Hello, Muffins. So, so, what we are trying to do right now is to implement basically the modulator of M17, and in particular is we are dealing with the first part of the demodulator, which is the so-called clock recovery. And it works like this. We are sitting on the radio, okay, and we are receiving an M17 audio stream, sorry, RF stream, and basically the M17 stream is a 4 FSK digital encoded stream. So we are receiving a stream, the actual modulated stream. So the radio is demodulating it in FM. So we will see something like, let me see if I can show you that by plotting. Mm, Okay. Okay, here we are. So I will share my screen too. So the radio is receiving something like this, that basically, so let's start from the beginning. This is the every M17 transmission starts with a preamble. So basically what we see at the beginning is a sign signal which is sampled with a sample rate of 5 samples per symbols. So let's consider these peaks as the symbols plus 3 and minus 3, right? Wojciech, correct me if I'm telling stuff which is plain wrong. Uh, don't fear of correcting me. So basically we have these symbols. So let me see, maybe if we go into the signal part, it's more evident. So yeah, so these are the +1, +3, -1, and -3 symbols that we are receiving from the stream, okay? But we are not simply getting a +1, a +3. We are getting many analog samples that interpolate between +1 and +3 because this signal was RRC filtered to have it to basically be limited in the frequency domain. So there are the problem to be solved is how to extract the actual symbols from this analog stream of samples and um, but so more or less this will be done in two steps. The first steps will be the so-called clock recovery. So we want to understand where in this stream are two things maybe mainly. When a M17 frame is beginning and when what is the exact alignment of that frame because I've said that we have five samples per symbol, which means that every symbol basically spans through five different samples. So if we can understand what is the correct alignment between 0 and 5? What is the offset basically? What is the sample which is more closer to the center of the symbol? Then we can just slice our input buffer of analog samples and take the ones which are most close to the to a symbol, and then we just have to basically understand convert an analog value in expressed in 12 bits into a value between which is either +1, -1, +3, or -3. Mhm. Yeah. So the f- so the first thing we have to do to this is actually this is synthetic. It's not the actual signal which comes from the radio, but we can, since OpenRTX can also compile on Linux, we will test all the algorithm on Linux where we can have the greater visibility on what's happening, and then if everything works, we will put it on the radio. So this is similar to something that we will receive from the ADC of the radio. So the first thing we have to do is we have to apply an RRC filtering on top of that. Um, so already have that, so I will enable just the plot of the RRC filtering. So the signal in orange is the RRC filtered signal, and maybe Wojciech, you can tell why the second, first application of the RRC filtering at the receiving side is needed. Mhm. Yeah. So now what I'm going to show basically in green is where we are right now. So we implemented the the computation of the convolution between the sync word, the symbols of the sync word, which are just, not analog, just plain symbols. So -3, +3, -1, and so on. But the exact sequence of the sync word, and the whole, basically, the whole RRC filter, the whole, sorry, Wojciech, please. Okay, so as I was saying, the orange part right now that we have is the RRC filtered input signal. If What we did now and what I'm plotting now in green. Okay, so yeah. So what we are seeing right now in green is the uh, okay. It's basically the correlation between the sync word and the RRC filtered input stream. But this correlation is not done with how is it done? Basically, it's a convolution, but while the input signal is uh, uh, in 5 samples per symbol, our sync word is just the symbol themselves. So to be able to properly to properly correlate those, we need to what we did was take the input stream and just select 1/5 samples. Then we go just one sample forward, but again maintaining this stride of just keeping one every 5 samples. This way we are already compensating for the additional sample rate of the input signal, and whenever we get the maximum correlation between the sync word and the signal itself, we will be sure that we found the correct alignment. So basically, which is the correct offset between 0 and 5, 0 and 4, for aligning the samples to the symbols. So that comes basically for free. And also, computing the correlation this way, as we clearly see from the graph, shows us some peaks which correspond to the beginning of new frames. So the first negative peak is the beginning of an M17 transmission, and the other are mark the beginning of an M17 frame. Is this correct, Wojciech? Yeah, yeah, definitely. It's an analog signal sampled at 5 samples per symbol. Let me switch to the code. So the code that we have right now. So I have here the implementation, which is actually OpenRTX code, so the code that will go straight into the radio, and which takes as input basically the samples that come from the from the ADC, which comes from the baseband, and on the other screen I have some test code. Let me check where it is. So here it is. Here we have some test code which basically is aims to test the modulator class, and takes a dummy, a real M17 baseband, but not one received from the radio, but one stored in a file, which is this one, and tries to basically uh, it injects it into the class as if it was the real stream from the radio, and then it tries to call the different methods, for example, to extract uh, the clock and the alignment, and to detect the start of a frame. So this is a dummy code. This is the real code, and this dummy code just it's a unit test which calls the real code from the demodulator, and stores the output in a CSV so that we can plot it. So if we can make this work, basically, then it's just a matter of hammering down some minor things, but it should work also on the radio. So let me see where we. One thing which I wanted to do is to, since right now we are doing the algorithm that is shown, the output that is shown basically in green here is what it's computed by this convolution function, which takes simply it takes basically an offset It takes the baseband itself is just a variable of it's an attribute of the class on which function this method belongs. So the baseband is implicit. We don't have to pass it as a parameter. And we have then the target and the target size, which are the sync word. Okay. So now this actually works, but it performs the computation using floating points. So one thing I wanted to do is convert this algorithm to you int 32 is basically to 32-bit integers so that when we move it to the radio we can go faster because this is actually a very time constrained implementation because the STM32 is not that powerful and also is we have strict time constraint to meet because when we receive an M17 frame, we have to process it fast enough to be able to basically to keep pace with the M17 stream itself. If we are to yeah, we have to do this real time. And also, this is not the only thing that the radio is doing while we receive an M17 frame. I mean, if we receive an M17 data frame, it might be, but if we receive an M17 voice frame, we need to take the resulting, the output of this. Basically the content of the frame and to pass it along to the codec 2 vocoder. And the codec 2 vocoder is resource intensive and takes time to process. So we need to be able to do this clock recovery and initial demodulation as fast as possible because otherwise we cannot fit the real-time requirement. So to conv so the convolution is actually it's a simple operation. It's just we take we take the samples from the baseband with basically an initial offset summed by um, I, which is our iterator variable, multiplied by M17 samples per symbol. So this samples per symbol makes it sure that we are selecting in this case of this input test file is 10. So this makes sure that we are selecting the first sample, then the 10th, the 20th, the 30th, and so on. But the offset, so we are computing this convolution for offset which increase by 1. So on the first run we are taking the 0, the 10, the 20 and so on. On the second run we are taking the 1, the 11, the 21. On the third run we are taking the 2, the 12 and so on. So and we for the size of the target, which is the sync word, we are computing a sum of product between the sync word and the baseband, and we are storing the whole sum in this convolution variable, which is actually what is plotted right now for increase. This basically is changing. We are changing the offset, and for every offset we compute the whole convolution. So, first thing I wanted to check are if we are using the right sync word because here we are getting positive correlation value, so this means that we matched it. But this one is negative, so this is not the correct sync word, but maybe is one which is just shifted with shifted logical value. Is this correct, Wojciech? Mm, yeah, yeah. Let me check which is the sync word that we are using, because when if we want to detect the start of the M17 transmission, we need to correlate this, right? The one which is negative right now. Okay. So now we are using. So I've put here three sync words, but the symbols are not correct. It's just that it's just a placeholder. But we need to recognize the LSF sync word, which will be this one. Then and then we have the stream sync word and the packet sync word, right? Or we just need the stream sync word right now. Okay. So what is the sequence of the LSF sync word? Okay, yeah, yeah, but is this correct? Because the two are equal. I just put a placeholder there. Mm. Also, the first there was a thing like the most significant bit is sent first. So it's like this, but we need to convert pairs of bits to symbols, right? Yeah. Okay, let me. Uh, yeah, yeah, yeah. Just a second. Okay, you should be able to see it right now, right? Oh, I picked the. Okay, okay. So, what is the symbol stream again? Okay. And now we discovered why the peak is negative, because it's exactly the opposite of the other one. Can you see from here? Okay. So now I can correlate with the LSF sync word. So if I go here, uh, okay, here I'm using actually a sync word, but I have to use LSF sync word. And I can plot both of them actually. And this will be the stream sync word. And we have to print it. So um, mm, mm, Okay. So the code is fine. Now let's execute it. Mm, So, oh, um, if he wants to join the on Jitsi, he's welcome. Do we have comments on on YouTube? Let me check. Mm, oh, we have some comments. Oh, definitely. Yeah. Every day is a good day to buy that radio. Okay. No, we are actually we don't take any money from Retevis, so it's just that right now is the radio that we are working the most on. Actually, the one that we are working the most is the MD380 or MD390, and the UV, you know, it's actually uh, may it it's a bit harder to mod because right now you still need a modification to make it modulate M17, but it's dual band and it's less unobtainium than the MD380. Yeah. Okay, so let me see if I can plot everything. No, I need to test Mason test. Fail, perfect, so as expected. Yes, it failed successfully. Uh, mm, mm. Okay, how did I call it? LSF convolution frame convolution. Oh, it works. Look at this. Yeah, look how beautiful that is. So, the first, the green one is the LSF sync word correlation, and the red one is the stream sync correlation. So we see the first one is green and the other one are red. And we just have to take maximum of the correlation to detect the corresponding sync word. Amazing. So I would now try to convert it to integer. So if I do it as early as possible, I believe that it's good. And to do so, basically, I wanted to proceed like this. So the function is this one. It's basically a sum of products. So I have to just scale everything down so that the sum of product fits into an uint32. And no, but there are also negative values. How can I do that? Do I have to use int? Silvano will be helpful right now. Ping him. Oh, okay. Okay, got it. So, um, if I use signed integers, I'm able to represent both positive and negative numbers, and I believe I have to do that. Otherwise, but wait. No, yeah, I need to do computation using signed integers because otherwise I won't be able to properly handle these both positive and negative numbers. So I have to use int 32t's. Okay. And the problem is that if I use simply an int 32t, I can count up to 1 to the 32. 1 shifted by left to 32. Let me use Python instead of my calculator. So the maximum representative range of 32-bit integers is, no, it's not this. It's signed, so it's 31. Is it this? Is it this big? Yeah. Yeah, it's over 9,000. It's extremely big. So, but the maximum correlation value that we can expect is 600,000. So we fit in. So I just replace float with int 32t's and that's it. So target in this case is an int 8t, int 32t. I can maybe do it this also with 16 bits, but for now, if we can make it work with 32 bit, that's fine. So the data, baseband data, well, let's convert it to int32t, sum, and everything becomes an int32t. Then, here where we are doing the convolution, uh, yes, yes, okay. Yeah, very nice. Yeah, also we are not dividing when we are doing the cross computation, so we don't. Yeah, we have integers all the way. Now, let me check again if it works. So I've just basically used the integers um, instead of floats, and I have to change also the other file. Okay, let me check. Okay, it fails correctly. I should put a return one for yeah, let's put a return one just for the sake of having it not failing correctly. But why is not there a return the modulator.h? This one. Why it returns zero? Return zero should be a correct output, right? Well, this is the same thing done with integers. So it's exactly like before, so it works. Let me see if... Yeah, yeah. It's identical to the previous one, so it's fine. We are plotting this file here. Actually, this whole code will remain as a unit test, so it will be performed automatically every time OpenRTX is built, and will I want to make it check with an example frame that the sync words are as expected, so that we avoid the regressions. See, yeah, as you can see here, right now are integers, the correlation value, and so yeah, we are plotting the right thing. Okay, so we did that. Now. Next step is to try to detect the peaks, I suppose. So you suggested me a nice algorithm, Wojciech, which is that we should keep a live computation, because all of this is done in basically, yeah, 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 yeah. So let's compute the standard average and plot it, I would say. And then should give us an idea of what is the expected deviation from of the signal. And so we can just pick, I believe we can plot that, and we can select either that or, a multiplication factor over that, the standard deviation, and see the values which are, let's say, more than 3 times the standard deviation, or so on. The We take only the LSF, so which is the green one. Now it's blue, but it's the LSF, as you can see. Yeah, yeah, but this is a false positive. Mm, 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 mm. No, we can do it even the standard deviation can be computed purely live. Um, uh, Standard, not even in a windowed way. There is the online algorithm to compute it completely online. Let me move this way. This one. Yeah, variance or I believe I don't know if we can do this with integers. Yeah, is the square root of this. Mm. Oh, because we don't need a statistical accurate one. We just need a rough measure of the. Let me just integer standard deviation algorithm. Let me see if the internet has something for us. Oh, he's using an integer division. Is it? Yeah. I believe we need that to rescale because otherwise it keeps growing up. You cannot do that without division. But this is the online version, right? No, is the online version. Oh, yeah, yeah, this one, this one. So let me have a look at this. So for X, this is the online version. For X in data, so we take the sample one by one. Here is incrementing n, which is the number of samples. We have an EX parameter, which is just the value, current value minus k. Oh yeah, I just did it. I just did it. There is already some code, but yeah, I wanted to understand it. And this code is exactly taken from Wikipedia, so it's just the same code. Mhm. Oh, no, you should be not muted. Try to talk. Let me check. Just give me a second. Can you see if you can hear yourself? No, I mean from an external stream of you on YouTube. Wait, wait. Hmm. Try now.
1, 2, 3, testing.
Can you see hear yourself from the stream?
Not yet.
Hmm.
Okay, I can hear it.
Okay, perfect. So back to what we were doing. So yeah, live.
Okay, Nico, I have to check my microphone gain. Is it okay?
Yeah, just lower it a bit.
Okay, testing again.
Yeah, now I believe it's fine.
Okay.
So we are having two values here, and we simply multiply the two, and we remove this. Yeah, okay, it's nice. We have a. I believe we can do. Is this basically implementing the same thing in integers? Uh, n times n. Oh, let's try if the Stack Overflow works out of the box. So, um,
Okay, so just for the record, I was here all the time. You just couldn't hear me.
sorry
So
for
hello
that.
again. Hello
So
again. This is 55
for yeah
WWT.
for everyone, it felt like I was talking with myself or with my other personalities, you know. So maybe Wojciech, you are just in my head. Okay, so if we want to compute the standard deviation, we need a state. So mm, how can we do that? We can just keep a state and keep adding samples. So um, live stddev. So we receive one sample and we put out the result of the live stddev. Okay. So what we need to do is we need a bit of a state variables. So we'll put those in the class itself. Let's do this. So let's start organizing stuff. Buffers. Baseband, analog values, frame index, state variables, live standard. And here we put unsigned the sum square sum and instead of doing this we simply do this update stddev, which is a void, and get stddev.
So how long do we want the window to be? So the n in the code.
What window?
The time window, because we can't just take all the past samples to calculate the standard
No,
deviation.
the standard deviation will be completely live, so the window will be one sample, one correlation sample. Every time we compute one correlation sample, update the standard deviation, check if it is a peak. And we can do this basically advancing one frame at a time. So when we compute the minimum number of frames necessary, and when we reach a peak, we simply switch to another state of the state machine in which we know that the next 49 how much are them? The next thought samples are the frame itself.
Okay, so let's assume that we are at a time point at around 2000 and we are at the peak.
Yeah.
So what would be the standard deviation value, or from which samples would you have to calculate it?
I will
Past
keep
samples.
I won't use past samples. I will keep a running state, a state, and I will update it with the current standard deviation. I will take, I won't decide this in advance with n past samples and go fetch them. I will compute it live, so every new frame updates the current standard deviation.
Okay, so my idea is to plot the standard deviation
Yeah,
on this plot.
yeah, I will do this right now.
Okay,
So,
because I think there's some flaw in this
why?
thinking. I don't know yet.
Okay, you have
So
a
I just
nomen.
finished it.
Okay, so I have two functions, update standard deviation and get standard deviations. The get standard deviation takes no parameter and returns the standard deviation, and the update standard deviation takes a sample and returns nothing and just updates the internal state. Okay, so now sum sample square sum sample per sample. Sum sum. Okay, does this make sense? I'm incrementing the sum. I need also a reset. Live standard deviation. Let's call it online.
So std def sum is going to increase ad infinitum, or not?
Um,
Line 88. You just add a new sample
yeah,
and we never clear that.
but so that was not actually the Stack Overflow algorithm probably sucks. Oh, okay. Can I tell Stack Overflow? Can I say Stack Overflow? Here, I believe this one actually is smarter because it does not saturate. But so we should find one which not does not saturate. Let's see.
I've got a strong feeling that this is a wrong approach.
But why? If we can do it completely online, we avoid the problem of looking in the past history. So we avoid the problem of keeping the past history.
But uh, we need something. We need to, just like in the line 88, you just added the new sample value. So at some
Yeah,
point
this
of
does
time,
not work. This does not work yet. But there is a way to basically to modify this code to actually scale down accordingly as more stream are. I just have to find it. I already used this in the past. Let me trust me on this. So, online, Welford online algorithm.
Silvano is not here, but I'm going to say what he would say. Wait, stop.
Wait, stop.
Yeah, that's what he said.
We love you,
Uh,
Silvano.
yes.
So it's often to the in a single pass, inspecting each value only once. Here it is. We don't
Mhm.
want we want an online variance computation algorithm, and it can be done. So the formula is this. You see, update and finalize. Oh well, we have the code. An example Python implementation of web for new value, compute the new count, new mean, the new M2. Mean accumulates the mean of the entire dataset, M2 aggregates the square distance from the mean. Count aggregates the number of samples seen so far.
Okay, but imagine a situation that there is some noise uh, for just a brief period of time in the baseband. So it's going to interfere with this algorithm. And
But
if we use the window, uh, we just
but you
can
are
ignore them.
completely. I believe that this algorithm basically um, does not keep infinite history because older sam like as in the square moving average. How is it called?
Okay, but
Moving.
the count is being incremented all the time, so it has to
Wait,
overflow.
now I'm doing the Silvano, but can so we need to. mm, So in this case, we are updating it in real time, but actually count is still going on. So we cannot reset it. Or we simply, whenever we get a new buffer from the radio, we reset the count. But we lose
Or
information
maybe.
about the previous history, which is helpful. Can one compute an online limited time window variance? Let's see. Moving standard deviation.
So why can't we use previous samples?
Because then we have to store them.
But that's like 40 samples. Okay, maybe more, but that's not a lot. And each sample is what? Int 16?
Yeah, if we otherwise we can just do that. But let me try a
Okay,
bit.
let's try.
Over a sliding window of 11K. Yeah, no. Okay. Also, if you take a history of 40 samples and you compute the moving average on over those 40 samples, it means that every time you get a new sample, you have to recompute all those 40 samples again.
Yes.
While if I'm able to somehow tweak this algorithm to not have it overflow on the count, I can simply basically uh, just do a single operation, update mean, update variance, and not simply not compute the square of 40 samples, but
Okay,
just
so
update 5 of them. So I believe this is the right approach. How to make it not overflow on growing number of counts? Well, apart that our count, if we store it in a 32-bit variable, it will overflow in a lot of time. No, maybe sometimes. How many we are receiving? Can you compute, you that are, good with math, Wojciech, can you compute in how many seconds do we overflow?
Okay, so the count is
This number is 1 to the, uh, no, 1 to the 31, sorry, because it's signed. So this much.
and why the count is signed. We can use
Oh yeah,
you.
unsigned. So it's this one.
Okay, so we increment the counter for each.
Each sample, so it's not each symbol but each sample, so we are sampling at 24 kilohertz.
In this example, yes, 48, but in MD380 we are going to use 24.
24
But okay,
kilohertz.
I'm taking 48 for this calculation. Okay, so 2 to the power of 32 divided by
One to the, oh
48.
yes, yeah, true to the power is this is a left shift but it's equivalent.
Okay, so that's 90,000,
Seconds.
I believe.
Yeah, if you are using hertz, then it's seconds.
Yes,
Okay.
correct.
But there still might be a way, you turn off the radio before it overflows. But I believe there might be a way to reset this. We simply reset all the things and lose history, but we start from scratch. For example, when we receive a new buffer, for example.
Somehow I don't like this idea. So going back to the windowed version, when we have an access to the past samples, we don't recompute. Uh, so let's say that the window is 40 symbols long. So that's 200 samples.
Hmm.
And if we are pushing 5 new samples into the buffer,
Hmm.
we push out the 5 from the left side.
Hmm.
We just discard it. So we don't have to recompute uh, for each sample, but only for those 5 new, because we can retain the last result of the multiplication in the RAM and
Hmm.
just add the values for the 5 new
So you
samples.
you take mm,
You
because
do
the
at the
standard
first
variance is actually the the value squared divided by the square mean of the population, right?
I think so. Yes,
Is the sum of that. No.
but we could just
So you
use
you store squared values instead of normal values.
first of all, in the first step, we've got 200 samples of the baseband. And in the first step, we have to calculate the average value. Okay?
Hmm.
So, step number one, we've got 200 samples. We calculate the average. And then for each sample, we calculate what is the square of the difference between each sample and the mean and the average. So that's step number one. And the result of this step is just the sum. We can divide it by 200 if you like,
Hmm.
but okay, this is step number one. And in the next step, we can uh, take out 5 of the oldest samples and
Hmm.
put in 5 new samples,
Hmm.
and then use the 195 uh, results from the previous step and just add the 5 new.
Okay, but so what about um, mm,
So at each step, we would have to remember the result of those 195 computations, the first
Yeah, but
part.
really look at this. Now, mm, forget about the count. The count is actually what? How is it actually used? Is the fact that the final result is scaled by count minus one because basically, so not all these values add up. We have a live update of the mean because we are here we have new value minus mean and mean plus equal delta divided by count.
Yes, so for if you are operating on integers, then delta divided by count is going to be zero, pretty
Yeah,
much.
yeah. No,
So,
that
so
sucks.
that's a pita.
Mm, maybe do we get some help from the YouTube chat?
The audience.
Yeah, from the audience. Can you check that?
No, nothing. No help. But I think the windowing is the key to this
Mm,
problem. So
mm,
we really have to access past samples.
mm, because so the count number is fixed. Mm, or we could simply use this. But this is actually done on a whole set of samples. It's not done on. It's not live. Well, okay, let's do this
Okay, but it
with.
says accumulator in the comments, so I don't like this word
Mm,
already
mm, mm. Why?
because it's probably going to overflow.
Well, it
Or
depends on
maybe
the
not.
window.
Okay.
Oh, this is just a square root. What am I looking for? Okay. Okay, then basically, so according to your approach, we can take a sliding window of samples.
Yes, last 200 samples.
Okay. And because I'm also worried about, maybe this can help us, I'm worried about the wraparound. So whenever we switch from this buffer to the next buffer, we need to stitch the two properly.
And is that a problem? Because
No, it's not a problem, but we need to, because the convolution is actually computed on the buffer itself. So at some point, it needs to. So we will have a problem 5 samples before the end of the, or how many are the samples of the. You know, when we are reaching the end, at some point the convolution would have to go ahead and jump to the next buffer, which might not yet have. But
oh,
let's
I
think
get it.
that later on. So let's solve first the standard deviation problem. So for the most efficient way to keep an history is a circular buffer. So let's.
But hold on. If we've got a full buffer of samples, then we can calculate
Oh
the
yeah, we
standard
can use the
deviation
buffer
for the
itself.
whole buffer.
Yeah, we don't need
Yeah,
additional history. So okay.
so let's try it.
So let's just do compute get standard deviation. and we will get so an offset. But also here we problem begins because we are not computing the standard deviation on the samples. We are computing the standard deviation on the convolution result,
Yes.
and we right now we are not keeping those.
So can we keep it?
So, yeah, but we need a circular buffer. We don't need to keep those for the whole frame. We just need a limited number of those, right?
Of filtered samples?
Nope. Of the result of the convolution, these values.
Let me think.
But
I
can we
think so
do?
because we are interested only in the peaks, so we don't care what's the value between each peak.
Can we do just a weighted exponential moving average, and we will just basically, if we tune the parameter properly, this thing can be done live. If we can
Well,
tune this down, we can have something like, you know, um, a low pass filtered version of this signal, something
but
like this.
but uh, taking
Oh
an
no, it will
average.
be an
So
average, so it will be like in the middle.
yes, we need the spread value, not the mean value.
Yeah, yeah. Okay. So, I shall keep a circular buffer of the last correlation values, the last, I don't know, 128 correlation values, and use those to compute the standard deviation over them,
Hmm.
and then plot that. Okay, so circular buffer will be this. Uh, just let me, just a second. Okay, so just we are storing in 32 T's convolution circular buffer. Um, how is the buffer long? Let's use a constant static context size the images. Let's start with 128, okay?
Okay, 24.
Why 124?
And why 128?
Because of is a power of 2. Everyone loves power of 2.
Oh, sorry. Yes, of course.
I thought you had a reason for that magic number.
I was thinking about 1024.
Oh yeah. No, I will start with a small one and then we will see. So since it's that small, I can use also a 16-bit variable to count the size. I believe I cannot initialize it here because Not sure. No, maybe I can. Okay, so we got the circular buffer. We got the index. We need the start and the end, right? No, no. We need just the index. If we are keeping the window size fixed, we just need the index, and then every time we advance the index and read from that to that minus one modulo the size. So standard deviation. Now, first thing first, we have to push the samples in the buffer. So every time we compute the convolution we store in the buffer. And now it comes the problem.
Mm.
Do we use the same buffer for all the convolutions of all the sync words? Because they will be more or less similar? Or do we keep separate buffers for all of them?
I think we need separate
Are you sure? Look
buffers.
at the signal.
Okay, looking.
In my opinion, the standard deviation is more or less the same. So I can even ideally uh, use the convolution from both signals and that's it.
I think the standard deviation would be even the same because there is just a sign change between
Yeah,
those two.
in this case, yeah, but does it hold more or less for all the other standard deviation? It's just a peak detection. We don't have to. We're just using that. Mm,
So yes, one buffer is enough
okay,
for
I will just
those.
keep all the convolution that gets computed. I will just push them in a buffer.
And this is just because those sync words are complementary.
Yeah, I was worried about the fact that if we had to extend this to another sync word which is not complementary, this would not hold. But you know, this won't be the case. So in a circular buffer, so conv circ buffer di conv circ buffer index. The index points to the first empty cell, so I store in that and then I post increment. Look how neat. And I need also to reset the. Oh, I love circular buffers. Look at this. 2 lines. And I just need to access from that position backwards. Okay, so I'm pushing the standard, the convolutions into that buffer. Now, so what was the formula for the standard deviation?
Uh, for in our case, it would be take the mean value and then for each sample calculate the difference, square it, and then take the average, right?
Yeah,
Maybe that's variance, but it doesn't matter for in our case.
so compute the mean first, and then for each sample we take the difference from the squared value of the sample with the square value of the mean divided by the number of samples.
No, you have to take the difference and then square it, not the other way around.
Okay.
So first the
And
difference.
and then I sum all those.
Basically, yes.
Okay. So it's the average of the difference between the average and the sample. And
Squared,
each
yes.
sample squared. Okay. So yeah, we compute the mean. So mm, now it comes the problems. We are summing 32-bit values. Computing the mean with only integers, it's a pain. Do I use floating points here? Yeah, let's start with floating points, then we'll think about that.
Okay, so we are going to perform optimizations later.
Yeah, I would first, premature optimization is the root of all evil. This is a quote by Donald Knuth, which is a computer scientist. Conv buffer. I need to go between. I need to sample from backwards from. Okay, so let's compute this. In I need conv jerk buffer index minus M17 conv buffer size plus I, because then it will be in case of 0 just this is the no, but this is not yet populated, so maybe -1. No,
Okay,
this
Nico,
is
listen, I
correct.
need to take a 1 minute break, okay?
Yeah, please,
Okay, I will be right back.
no problem. died. Okay. It's not failing successfully, so this is a real fail. I have to understand why. So mm, M17 modulator dot standard deviation mean accumulator. Let me rerun the test. Oh, it died. Where it died? 103. Fprintf. Standard deviation inline 90. Accumulator plus equal com 0 buffer index. Oh yeah. Silly me. Okay. This is not a live stream, it's becoming a marathon. We are live streaming the whole implementation process. 2 months of live stream. Did it fail correctly? Yes, this time it failed correctly. So, plot. Oh, that is the mean. Okay, clearly something is wrong. Uh, Let me see.
0?
Yeah, it shouldn't be 0. Oh, no, yeah, the mean might be 0. Maybe it's not exactly 0, but
So it oscillates around 0. That might be the case.
let me take the CSV. Take a look at the CSV.
And I think we should
No,
take
it's just 0.
constant 0.
No, it shouldn't be like plain 0. Probably might be something slightly greater than 0, but it's truncated down to 0. Let me try with float before.
And we don't really need two convolution plots. You can just take a look at one for the link setup frame,
Okay, I will fix
just for
that.
readability.
Yeah. Okay. How many viewers do we have?
3.
Okay.
It says 3, but we've got 7 thumbs up.
Mhm. Okay, so this becomes an F, and this becomes a float. I enjoy the idea of streaming. I'm if I'm chill and I have time to do that, and so why not? Making enabling people to take a look at how this is done internally.
Like in the kitchen.
Yeah. No,
Yeah, so
it's plain 0,
welcome
so
to
it's
our.
something is wrong. Should be different from 0. So we are computing the convolution. Now we'll remove the other plots. Let's see, just that. I expect the first 128, since that buffer is initialized to 0, at the beginning, for the first 128 samples, the mean should be 0, but later on it should not. Oh, yeah, I'm not increasing the conf circ, but no, yeah, I'm increasing that. I'm increasing and also using the modulo, so it should contain now config buffer index minus M17 plus I. Mm, I can't find my error. Accumulator equals 0. Accumulator plus. Let's do one thing. Printf debugging. When necessity calls. Okay, so okay. Oh yeah, look at this. Mm. Oh, so the samples are being populated in the array.
Oh, what's that?
You see? These are all the is the content of the circular buffer, which should be increasingly filled after being like completely filled. So maybe the mean is really 0. Look at this.
No, it can't be exactly 0.
Oh yeah, it is exactly 0. You know why?
Yes, because we've got alternating values,
Yes,
positive and negative.
exactly alternating values. Now I will mute myself and swear. Okay.
You can also swear in Italian.
I will mute myself and swear in Italian.
That's right.
Okay, now we should go. What a coincidence. Uh, um, let's just do 0. Okay. Oh, now there it is. This is the mean. Okay, makes sense. Now let's compute the standard deviation. So this is the mean. Now we have to, for each of those samples.
Okay, so after 18 minutes of streaming, we've got the average value.
Sorry, I'm slow. Um, okay. So again, can I do this? I cannot do this live, right? I have to do this in 2 passes. Why that is statistics so computational intensive? So now I need to. So I compute the mean. Standard deviation will be just positive.
Mm-hmm.
Okay, now so I cannot I have to solve the problem of the fact that is using both for computing the standard deviation. Okay, the mean is computed. Now I need to perform the square of the difference between each sample and the mean. So I need this. Int okay. And I need an accumulator for the standard deviation.
I believe so.
So I can use the same. No, I need another one. So okay. So plus delta times delta divided by the number of samples.
Uh,
Um, let me check. Sum for an entire population of size n. This is our window, n is our window. No, so I don't need to do this sample by sample. I just need to sum all the values, sum the square of all values, okay, and subtract the square of all values, the sum of the square of values with the square of the average.
Divided by n.
Divided by, yeah, because this is always this is already the average. It's just that the sum squared. Okay, so I can do this in one for loop. So I have to compute the accumulator, then I'm squaring the accumulator divided by n, and also I am computing the sum of the, okay, so this is the accumulator. Then I have also to compute the sum of squares.
I
That's
think
correct.
there's a small flaw in the code in line 101 when we subtract the mean, but the mean value is not constant over the window, right?
No, wait, this is still wrong. Don't trust it. Just give me a second. So sum squared the sum. I'm taking the sum and the squared sum. So this is the sum. The squared sum is just the sum of the squared values.
Is it?
Okay, now this becomes a float. Okay, I have the sum and the sum of the squares.
Uh,
Now I don't have
the
to
sum of,
compute the matrix.
listen, the sum of the squares is not the same as the square of the sum.
Exactly. The square of the sum divided by n, the sum of the squares minus the square of the sum divided by n, everything else. So sum of the square minus sum square of the sum divided by n. Okay, I believe this should work. Do you agree?
Let's check it.
No, there is a problem. The minus takes precedence, so it should be this sum square of the sum of the squares minus square of the sum divided by size is exactly this formula. So let's check it. This should already this is a division, then I'm casting to integer, which is almost useless, but
The last division can be omitted, I guess.
let's check. So did it fail? 124. In which file? Well, failed successfully. Perfect. So let's see. Oh, nice. This is huge. Why it is so huge?
Because we have a lot of squares to sum.
Yeah, but it doesn't make sense to. We need the square root of this.
No,
Yeah, this is the standard deviation. Is sigma square. This is the variance. It's not the standard deviation. Standard deviation is square root. Let's go down
okay,
to the rabbit hole and then we will optimize this. So let's just use floats for now.
but those numbers peaked at around 3.5 times 10 to the power of 7, and that's a lot. So squaring that won't make it a lot smaller.
Or so maybe let's check with floats. Maybe it was just a rounding error. So f. Okay, they are even bigger. No, this is with floats. With plain floats.
Hmm.
That one of before was cast to one side, so it probably it was a bunch of overflows. So let's try to square this thing. Um,
So the orange plot is for the standard deviation,
yeah.
and that's line 95?
E- 96, yeah.
Yes, 96.
Yeah, it was 95 before, sorry, I moved it down to add libmat. So let me check, it failed successfully. Now let's plot. Oh, yeah, now it makes sense. This is the standard deviation and it makes lots of sense. Fucking hell to compute, but
And now what? We have to check if the peak is
let me
above
let me do
2 times
2 times, yeah.
or 3. We need to check that, maybe even more.
Oh, this is 2 times. Not enough. I should say 3.
I see your screen after some lag, so uh, yeah, 2 times is not enough.
This is 3 times. 3 times could be nice, but this is a false positive. So maybe 4 times. This is 4 times. I believe we are screwed. Ah, we need something like. But is this fine tuning really? I mean, I believe it. I think it will break. We do something like 3.5. But what if the input signal changes? Hmm.
So in this case, we are using an ideal signal, right? With no
Yeah,
noise.
and also this is not yet, this has no DC bias. You know, there's a very little peak which is visible, and this is inside. So and this is outside. But
Oh, we are we are not so fucked.
no, no, we are fucked. What about we increase the number of previous samples to 124 maybe, or we reduce it because we need it. Let's see what changes.
I think we have to increase it
Now it's 124.
because, in some sense, this is a low pass filter.
Oh, yes. This is nice. Let me just increase it even more. Yeah, this is a monster of computation. It's a for loop over 2000 values and float computation. Yeah, it will be hard to optimize, but we'll do that. No, okay, but yeah, this is not
We are
really.
going to ask Silvano, just
Yeah,
for the record.
this is good, I believe, but maybe also 124 it's enough.
Yes,
Yeah,
because
Silvano, please
it also.
optimize it. We've done that. Please optimize
Okay, goodbye.
it. Bye. Lol, thanks, bye. This is perfectly fine. All the other pics are below, and our is clearly uh, on over.
So this
Um,
is for 4 times the standard
3
deviation.
point, 3.5, but we can use 4 maybe. We can still be. Yeah,
So in the end, we need to use an integer value for the.
yeah, we can do In the end, we can do uint 32t, and it's fine. But just for the final multiplication.
Mm-hmm.
Like this. Okay. This is with integers. Oh, why it sucks now? Hmm. Hmm.
It looks totally different.
Yeah, shouldn't. I'm baffled. That standard deviation value was already could already fit into a uint 32t.
And if we removed that 4 times
Yeah,
from this
that will
line,
be just a scale down. Let me do this.
but just to see if the shape of the plot is the same,
Yeah, yeah. This is just a multiplication, so I believe it will be the same.
because we are just casting one value
And
to another.
multiplying, yeah. No, it's just the same. Let me roll back. Just return the float. Maybe I did some silly mistake. Float, float. Four times.
All right, the return value was set to float when we returned int.
No, I just changed it right now. Oh, I know what I did. Yeah, I'm a silly boy. Basically here I just used the undo and I rolled back the buffer size to 128. Oh,
Nice
undo
catch.
is dangerous. Okay, so this is 4 times int 32t. Okay, float. Like this, and this is 124, 1024. This is a D, and now everything should work as expected. Amazing. Okay, and so we could simply, for each sample, compute the standard deviation, and when it is bigger than, basically, the value of the correlation is bigger than 4 times its standard deviation, what we can do is we can see we know that from that same offset we can expect a start of an M17 frame. So we can
Yes, that's
slice.
correct.
So we can
Hmm.
slice. Okay. I would say that we can stop here with the stream, and we will think offline about how to optimize this, how to do this insanely. Is there a way to? Mm, Yeah, we need a way to basically to do this, even a more approximate way, but to do this faster because I believe it won't fit the timing requirements like this. But it's just a feeling.
Hmm.
Like something like taking just yeah, I don't know. We have to think about this. And maybe the absolute value of the samples and use a low pass filter on that.
Maybe we need Silvano's help.
Yeah, and then from that on, it will be a matter of slicing and but first of all fixing the wraparound between buffers because right now the con which I believe because the correlation right now looks back into the looks ahead into the buffer by some set of samples. So whenever we are at the beginning, we are fine. Whenever we up until more or less this point, we are fine. And then we at this point, while going forward, we need to go into the next sample, which is not feasible. So probably what we should do at that point is we should discard the current buffer, keeping just those last samples, and use the new buffer, but starting from those previous samples. Because we cannot recognize a full frame if that condition means that the sync word is not fully contained into this frame, but it is halfway before and halfway after, so we need to go use the next buffer, but still recover those frame from the previous buffer.
That's right. Yes.
Okay, so let's thank everyone which attended basically this live stream, and we hope that it was I won't say entertaining, but at least different from your usual Saturday morning. And thank you, Wojciech, for being here, and
Thank you, Nicola.
see you next time.
Okay, see ya, guys.